Okay, let's now move on to the next one. So we've got iron and water going to iron oxide and hydrogen gas. So same deal here. We write down our reactants over here. So I'm going to now look at our mass. So we've got 40 grams and water we have 16. So I convert these now to moles. So moles is equal to mass over molar mass. Moles is equal to the mass, which is 40 grams, divided by the molar mass. So then we divide this, so we go 40 divided by 55.8. So we punch that into our calculators, and that will give us a total molar concentration of 0.716. Now again, we need to take into account this coefficient at the front here. So we go 0.716 divided by 3, and that will give us a total of 0.239 moles. Now we do the exact same thing for water. So we go moles, mass, molar mass. Moles is equal to the mass, which is 16 grams, divided by the molar mass. And that will give us, so we're going to have 16 divided by 18. So this is going to give us a total molar concentration of 0.88 mole. Now, we take into account our coefficient at the front here. So we divide this by 4. And our total molar concentration is 0.222 moles. Meaning that in our reaction here, it is water that is limiting. Again, very easy to fall into this trap because again, look at the sheer difference here. If you did not divide by the coefficient, then you would choose iron, which would be incorrect. Okay, moving on to our next one, and now's when we start to introduce a little bit of our theoretical and actual yields. So, silver metal is recovered during the reduction of silver nitrate. So we have silver nitrate here. During an experiment, 125 grams of copper was placed into a container or solution containing 275 grams of silver nitrate. Now, out of that, 135 grams of silver was recovered. What is the percent yield of silver obtained? This is where students get very confused because they go, well, okay, we're given the mass of silver, so it means I don't have to calculate that. And that's not correct. Because remembering what we've been doing thus far, like with our previous question, we were calculating the total moles or the total mass, all that sort of stuff. That is called the theoretical yield. The actual yield is what happens when we go into the lab, we actually conduct the experiment, we weigh it, and we go, aha, we got this amount of product. So this here is our actual yield. So what we need to do is, in order to find the percent yield, remembering that our percent yield is equal to actual over theoretical times 100. So we now need to calculate our theoretical yield in order to get the total percent. So how we do this? So we see copper, and we know by the question here that copper is 125 grams, and it was placed into a solution containing 275 grams of silver nitrate. So we now calculate the total moles of each of these, and we find out which one is the limiting reactant. So we go moles is equal to mass over molar mass. So the number of moles is equal to 125 grams over the molar mass. So it's going to be 63.5 grams per mole, meaning that the total molar concentration will be 1.97 moles. Now, because there is no coefficient at the front here, and this equation is already balanced, that is our final molar concentration. Now we repeat the exact same step, but for silver nitrate. So we now go 275 divided by 169.87, and that's going to give us a total molar concentration of 1.619 mole. However, again, remember this coefficient. So we divide this by 2, meaning that our total molar concentration is 0.809, meaning that the silver nitrate is clearly the limiting reactant in this process. So what we do is, this is the one that we're going to use because it is the limiting. So I'll just draw a bit of a line here so we don't get a bit confused. Now, our goal, what we want to do is, we want to determine the mass of silver. So we know that the number of moles of silver is going to be 0.809. Now, because of the coefficient here, so this has a 2, we now need to multiply this by 2. That will give us 1.619 moles. Now we work our way back to mass using moles mass, molar mass. So again, we rearrange this, we move this to the other side of the equal sign over here, and that will give us 1.169 multiplied by 107.9 grams per mole, which means that the total mass is going to equal 174.63 grams. Now, that's all well and lovely. We've found the mass. Awesome. Thumbs up. However, that's not what the question is asking. Whenever we finish calculating something, we go back, we look for our square brackets, and we go, okay, did we answer everything in there? So we scan through our brackets and we go, what is the percent yield? Okay, we don't have the percent yield, but we look at our formula. Do we have the actual yield? Yes, that was given to us over here. Do we have our theoretical yield? Yes, that is what we just calculated here. So now we can use our percent yield formula to get our percent yield. So I'm going to do that just over here, seeing as we're running out a bit of room. So we have our percent yield equals to actual yield over theoretical yield multiplied by 100. So the percent is 135 grams divided by our theoretical, which is 174.63 grams. Therefore, if we punch that into the calculator, we will get 77.3% yield, which is pretty good. So that means that out of the absolute maximum possible amount, we made 77.3%. And that is how you do percent yield and limiting reactant questions. So let us look now at page 186, question 38. So again, pause this question, give it a go yourself, and press play, we'll work through it. So, the methyl alcohol used in alcohol burners combines with oxygen gas to form carbon dioxide and water. Now, a bit of a pro tip here. Whenever you hear of something being set on fire, ignited, combusted, explode, flames, something like that, that means that it's being burnt, and any sort of combustion will need oxygen. This is why if you get a tea towel on a small flame, you can smother that flame and it will go out. So how many grams of oxygen, so I'm going to put a square here, are required to burn 60 ml of methyl alcohol, and that has a density of 0.72 grams per mil. So what I'm going to do here is our methyl alcohol combines with oxygen gas, so plus O2, and that's going to react to form carbon dioxide and water. Now, I see a bit of a problem here because we are not balanced, okay? We have four hydrogens and 2 hydrogens. So remember, we've got to always check our equations, and that means we now need to balance this. So we have 1 carbon on the left, 4 hydrogens, and 3 oxygens. And on the right-hand side, we have 1 carbon, 3 oxygens, 2 hydrogens. So this one doesn't seem too bad. So we need to just balance up our hydrogens here. So the only way we can do that is by adding a 2 to the front here. And that's going to change our hydrogens from 2 to 4, because 2 times 2 is 4. But that's also going to change our oxygen amount. So we've got 2 times 1 is 2, and plus 2 is 4. Now, we can see here that has created an odd and an even. So again, the best way to get around that is to multiply everything by 2. Okay, so we can see here our carbons balanced, our hydrogens balanced, our oxygens on the other hand aren't balanced. So all I need to do is change this to a 3. And that will then change our total number of oxygens on the left-hand side to 8, meaning that we have a nice balanced equation. Now that we've balanced it, we can now proceed with our calculations. So the question is asked how many grams of oxygen. So grams of here is required to burn 60 ml of methyl alcohol. So we have 60 ml, but we need again to convert this to moles. When we're comparing anything, we need to turn it to moles. So how do we do this? Because we have a volume. We don't use volume in moles because we have a mass and we have a molar mass. So this is where the gears should be turning and going, okay, what is the link between the volume that we have and converting it into a mass, which we can use in moles? And the answer is our density over here. So we have our density, which is 0.72 grams per mil, is equal to the mass, which we don't know, that's what we want, over the volume, which is 60 mil. Now, I've had a few people ask me, why don't I use volume in liters? So I know with other equations, it's like, oh, you must use it in liters when we're looking at volume. Why don't we do that with density? And the answer is, if we have a look at our units here, we need to keep this consistent because this density is 0.72 grams per mil. So we need to keep that the same. If that said grams per liter over here, then yes, I would have to change this to liters. But because it says it over here in mil, I can keep it in milliliters. So we rearrange this. So we move this over to this side. So it's 60 times 0.72, and that will give us a total mass of 43.2 grams. So now that we have our mass, we can now push through and convert our mass into moles so we can compare it to use with oxygen over here. So we go moles is equal to mass over molar mass. Moles is equal to the mass, which is 43.2 grams, divided by the molar mass. So again, we use our periodic table. So 12 plus 3, 16 plus 1, that will give us a total molar mass of 32, meaning that our moles is equal to 1.35. Now we need to take into account the coefficient. So we go 1.35 divided by 2, and that will give us a total molar concentration of 0.675 moles. Now we can use our moles to have a look at how much oxygen that we will need. So, sorry, this is a little bit all over the place. I'm running out of room. So we can see here that the coefficient for oxygen is 3. So it's going to be, so the moles of oxygen is equal to 0.675 times 3. And that's going to give us 2.025 moles. Now we convert our moles into mass because that's what the question is asking for. How many grams? So we go 2.025 mole is equal to the mass, which we don't know, divided by the molar mass. So the molar mass for oxygen is going to be 32. So again, we rearrange this. So it's 2.025 multiplied by 32, and that will give us 64.8 grams. So what that means is, and again, I like to do this as well. I say the answer and I put it back in the question. So it means that in order for us to ignite 60 mils of methyl alcohol, we will need at least 64.8 grams of oxygen to ensure that all of it combusts into carbon dioxide and water. Okay, so let us now move on to our next question here. So the question states 3 chemical reactions that lead to the formation of sulfuric acid are here. So we've got reaction number 1, reaction number 2, and number 3. So starting with 100 grams of sulfur. So it'll be up here. So we have 100 grams. How many grams of sulfuric acid will be formed? So it's asking for how much our final product will be. Now it says assuming a 10% loss at each step. Okay, so that's interesting. So it means after each of our chemical reactions here, we are losing a total of 10%. So that's something we do need to keep in mind. And it's also asking what is the percent yield of sulfuric acid. And we can now, let's hook into it. Let's start to figure it out. So the first thing we need to do, I'm actually going to just denote this as 1, 2, and 3, just so you can see where my calculations are going. So the first equation here, we obviously need to use our sulfur to calculate our total products, because this product will then become our reactant over here. Now, we're going to assume that we're going to have oxygen in excess because we're not given any information about oxygen, and it's safe to assume that that oxygen is just coming from the air, it's just exposed in a container. So the first thing I'm going to do with equation 1 is I'm going to calculate the number of moles of sulfur. So if we have a look on our periodic table, we can see that the molar mass of sulfur is 32 grams per mole. And we also know that oxygen is 16 grams per mole and hydrogen is 1 gram per mole. So we're now going to calculate the number of moles of sulfur. So we go moles is equal to mass over molar mass, which means that we're going to have 100 grams of sulfur divided by, because it's just sulfur, it's 32. And that's going to give us a total mole concentration of 3.125 moles. Now we use this again to work our way backwards. So we know that we have 3.125 moles. So now we're going to calculate the moles of sulfur dioxide. So we have the moles, which is 3.125, is equal to the mass, which we don't know, divided by the molar mass. And we move it over to the other side over here. And we move it to the other side over here. It's going to turn into a multiply. That's going to give us 200 grams. Now, this is where we need to be a bit careful here because of what this question says, is it says assume a 10% loss in each step. So what I'm going to do is I'm going to look at this and go, okay, this is our final calculated maximum amount of product, our theoretical yield. But it says we got to assume a 10% loss. So I'm going to minus 200 times 0.1. That gives us a total of 180 grams of SO2. So we can use this mass now to feed into here. So now we look at equation 2. So I'll name this C and D. So C, we have 180 grams. Now, we need to be careful here. We can't just sort of steal all the information we got up here because it was a 10% loss. So we need to go through and recalculate it again. So we have 180 grams. So moles is equal to mass over molar mass. So moles is equal to the mass, which is 180 grams, over the molar mass. So we have 16 times 2, which is 32. And we have the molar mass of sulfur, which is 32. So that gives us a total molar mass of 64 grams per mole. So 180 divided by 64 grams per mole, that will give us a total of 2.8 moles. However, something we do need to be mindful here is that when we looked at our equation B over here, okay, this was 1 SO2. However, over here, our coefficient at the front here is 2 SO2. So that means that this total molar concentration must be multiplied by 2, and that will give us 5.625 moles. Okay, and that is for C. Then what we do is we move our C over. So we have 2 SO2. So now that we've calculated the number of moles over here, we can now calculate our number of sulfur trioxide. Now, sorry, there was a slight typo there. It actually wasn't balanced properly. So we have 2 is to 2. So that means that it's a 1:1 ratio. So we're fine. So we now know the number of moles of 2SO3. So moles of SO3 is equal to 5.625 moles. So we go moles is equal to mass over molar mass, which means we have 5.625 is equal to the mass, which we don't know. So the mass is X divided by the molar mass of SO3. So we have 80 times 5.625, which means that our total mass is going to equal 450 grams. Now, again, we need to take a 10% loss. So we're going to subtract 450 times 0.1, which means that our total mass is going to be 405 grams. Okay, so what I've done is I've just deleted all the working out because I was running out of room, unfortunately. So now we move on to our very last part here. So we know that we have 405 grams of SO3, and now we can move on to our final step of finding out how much sulfuric acid we have. So 405 grams, what we're going to do is we're going to go moles is equal to mass over molar mass, which means we're going to have a total molar concentration of 5.06. Now again, we need to pay attention to our coefficient. So we can see that we have a 2 over here, but we only have a 1 over here. So that means we need to divide this by 2. And that gives us a total molar concentration of 2.53 moles. Because again, the total mass here, 405 grams, is 405 grams of 2 lots of SO3. So because over here we only have 1, this is why we must divide that molar concentration by 2. So what we do now is, again, we can now bridge this over here. So again, we have a 1 is to 1, so we don't need to worry about changing this molar concentration anymore. So we now go to calculate the moles and eventually the mass of sulfuric acid. So the moles, which is 2.53 mole, is equal to the mass, which we don't know, divided by the molar mass. So again, we rearrange this and solve for x, where the total amount of mass of sulfuric acid is going to be 248 grams. Okay, so that was a very hectic question. It was very full on. We did a lot. But we're not out of the woods just yet. Because in order to calculate the percent yield of H2SO4, this would be our actual yield. Because it's going, assume a 10% loss in each step. So that means that they've figured it out. They've gone, okay, during our actual yield, there is a net loss. So the maximum they can get is 90% worth. So that means in order to calculate the percent yield of sulfuric acid, you need to go through this entire equation again, except you do not do this step here. Okay, so you don't take 10% of the mass. You will simply just use that original mass. So in this one, instead of being 180, that would be 200 grams. And you would repeat through the entire thing again. So that means that how many grams of sulfuric acid will be formed? We would form 248 grams. Okay, so our next one is page 186, question 55. When 12.82 grams of a mixture of KClO3 and NaCl are heated strongly, the KClO3 reacts according to this equation here. Now, we've got a bit of information down here. So the sodium chloride does not undergo any reaction. So this is why it's not involved in our little chemical reaction up here, because it doesn't do anything. It doesn't contribute to the reaction at all. So after heating, the mass of the residue, so the residue is potassium chloride and sodium chloride, is 9.45 grams. So assuming that all loss of mass represents the loss of oxygen gas, calculate the percent of potassium chlorate in the original mixture. So what we do is, what we need to sort of ask ourselves is, we know that the total mixture here is 12.82 grams. Now, we remember the law of conservation of energy. So energy cannot be created nor destroyed. Energy and matter cannot be created nor destroyed. It can only be converted from one form to another, which means that mass doesn't just disappear into the air. It has to go somewhere. So because we know that it must go somewhere, we can determine the mass of our oxygen, because it says assuming that all loss of mass represents a loss of oxygen. So that means that if we know that our initial mass was 12.82 grams, and we know our final was 9.48 grams, that gives us a total of 3.37 grams of oxygen. Okay, so now that we know the mass of oxygen, this is when we can start to answer the question. So calculate the percent of potassium chlorate in this original mixture. So the first thing we need to do is we need to get our mass over here. So we do this by converting our oxygen into moles. So we go moles is equal to mass over molar mass. So which means our total mole is 0.105 moles. But again, coefficients. We need to look at this 3. So we go 0.105 divided by 3, which will give us a total molar concentration of 0.035. Now we can use this to calculate the amount of potassium chlorate. So we go moles is equal to 0.035. Now, potassium chlorate has a coefficient of 2. So we multiply this by 2, which means that we have 0.07 moles. Now we move this into mass. So 0.07 moles is equal to the mass, which we don't know, over the molar mass. So we need to look at potassium, chloride, and oxygen. So we rearrange this. So it's going to be 122.6 plus 0.07 moles. And that will give us a mass of 8.6 grams. Okay, so that's all well and good. So we've got our final mass of potassium chlorate. Awesome, fantastic. But the question's not done yet, because it says calculate the percent of potassium chlorate in the original mixture. So we know that our mass of potassium chlorate is 8.6 grams, but we were given at the very beginning the total mass of this mixture. So the percent of potassium chlorate is going to be our mass here. So it's going to be 8.6 grams divided by the total mass, which is 12.82 grams, multiplied by 100. So if you punch that into your calculator, you will get 67.2% of potassium chlorate in our original sample. Okay guys, so that finishes up Module 8, Video 2 of this series. Thank you all very much for watching. Hope you all enjoyed it. If you could all please fill out the survey down below, it really does help me a lot. As I say after every video, I'm not the one who uses these videos, you are. So I really want to get your feedback on these. Make sure that you guys are enjoying these videos, and if there's anything that I can do to help improve or make these videos better for your learning. If you do have any questions or queries, hit me up on my email at b.grant@griffith.edu.au. Keep up the hard work, guys. Best of luck in all your studies, and I'll see you all next time.